Alrighty folks, we're back with some more controller testing. Now, if there's one thing that I have to say when I start doing these designs and tests is that there seems to be always something to learn. Now, I also seem to be the kind of person that needs to learn it 3 or 4 times, and generally the hard way, before the penny drops. Now, I had hoped to improve the lighting. I went to my local electrical shop and I asked them to give me a 58 watt fluorescent fitting with a high frequency ballast. They gave me a 58 watt fluorescent fitting with a friggin' choke and starter, so that really hasn't helped me too much here, but I get a HF ballast for it. Anyway, enough about that. The controller has gone through a little bit of a redesign. Basically, what I found was that when I had my oscilloscope across the switch and I started to increase current, a couple of strange things started occurring. Now they're not strange, they're just normal artifacts when one starts messing about with power electronics, but it was just interesting for me to see the effects that were actually taking place. Now, previously, as you may recall, I had 4 of the let's see, we'll wind this thing down a bit. We had 4 of our C4DE capacitors set up here, and the capacitors were on their own separate bus bars that were linked into the bus bars that are bolted onto the transistors. Now, the inductance of those bus bars basically was causing the controller to ring like a bell at much above 100 amps of motor current. So much so that the magnitude of the ringing was actually threatening to turn the device back on. Now, if it had managed to do that, it would have been boom shakalaka time. So I messed about a little bit with some small capacitors, just putting them in, sitting on top of the bus bars and so forth, and basically came to the conclusion that I had screwed up. I had screwed up in my placement of the DC link capacitors. So I went ahead and decided to go back to what I knew worked, which is where I mount the capacitors directly onto the bus bars in between the IGBT modules. And fortunately, that actually solved 99% of my ringing problems. Now, once I had that out of the way, today decided to give the controller a test with the inductor bank, and at about 130-140 amps on motor current, the IGBT driver, which by the way is a VLA 500-01R, kept shutting down on desaturation detection. Now, just as a little kind of an I don't want to try to get too deep into this here because I'm probably already boring people beyond death, so I'll try not to get too much involved in it. But desaturation detection is a way for the driver chip, which is this big black dude here, to detect when there is, well, when there is in general an overload condition. That is where the transistor, when it's conducting, if my memory serves me right, should have a voltage drop in something in around 2 volts when it's fully switched on. I might be wrong about that, so feel free to correct me. But if that voltage increases beyond a certain threshold or fails to reduce down from the bus voltage to 2 volts within a certain period of time, the gate drive to the transistor is removed in order to protect it. Now, what was happening was that I had, prior to discovering the problem with the capacitors and bus bars, I had mistakenly believed that my problems were down to the switching speed of the transistors. And I had gone in there and I'd been changing the turn on, turn off resistors. But I had been using 22 ohms for both turn on and turn off. Well, what was actually happening was, now that I had the capacitors doing what they should be doing, and we came along and the transistors weren't turning on fast enough, and that was causing the desaturation detection to kick in and shut down the devices. So we changed from a 22 ohm turn on to a 16 ohm turn on, and that solved all that problem. And today we've progressively increased up to about 550 and 50 amps motor side current without any problems. Well, without any significant problems anyway. So very happy with that so far. So what we'll do is just very quickly do a little, let's see if I can get in there just with the phone here. I'm just using an old camera tripod here just to try to keep the Blair Witch stuff to a minimum. Oh, by the way, there's the inductor bank. You would have last seen that a few years ago when I was testing the new 500 amp liquid cooled controller. We'll do a bit more on that at a later stage. So inside in our controller here, as I'm hoping we'll be able to see, here we go. We now have 2 of the C4DE capacitors mounted on some aluminium standoffs just to thread into the capacitors and to thread into the bus bars, and they're now as close as I can physically get them to the DC rail on the controller. And we have gone from 4 to 2 of these capacitors. As to whether now I'm going to have to add in some more capacitance at a later stage, I'm not certain. I am noticing some drop in the DC link at high currents, so that might be something that we need to look at. Now, we've also gone up to 70 square cable just for the testing. As I say, we're simulating the motor with this bank of inductors. This is a 3-phase filter from an Emerson UPS, and they're capable of a lot of amps, even more so when they're in a bucket of water. So I'm just not sure if they would saturate if I tried to push 1000 amps through them. I kind of think they probably would, so I may not do that. It would be one surefire way to test the desat detection, but I'd rather not do that at the minute. Everything else on the control side is the same as previously, so I won't bother going through that. We've upgraded our crappy starting battery to 8 Calb CA180 Fi cells for nominally about 25-26 volts. Now, some people have said to me before, well, how come you test the controller at, you tested at 24 volts or something, and how can you have any confidence in it then when you're going to run it in the car at anything from 150 to 200 volts? Well, it's actually not anything to do with the DC bus voltage that we're concerned with here. Yes, there is the issue surrounding power, which obviously needs voltage and current, but what we're mostly looking for when we do these bench tests are a few things. We're looking to see how the transistors are switching, and we're looking for specifically the problem that I did have, which was bad DC link design, and that would have definitely blown the controller apart the first time that I would have given it any serious throttle. So very glad to have caught that. Now, what we're looking for then is the magnitude of the turn-off spike on the switch. Now, to put that in a bit of perspective, what that means is that when the transistors turn off, there's an inductive kickback, and that creates a voltage spike that adds to the DC link voltage. Now, this is why testing at low voltage is very important. If we simply slapped this on a 200 volt battery bank and gave it socks, and the magnitude of the spike was, let's say, 4 times the DC link voltage, well, I would be creating 800 volts across a 600 volt transistor, which is bad. So that would blow the thing apart. But if I test it at 12 volts and I get 4 times the DC link voltage on my spike, so what? Currently, the magnitude of the spike is about 1 to 1.5 times the DC link voltage, so I'm quite happy with that at the minute, because even if I run the controller at 200 volts and I get a combined voltage of 350 volts, 400 volts on the spike, so what? They're 600 volt transistors, they're not going to have a problem with that. So that's why we do our initial testing at low voltage, to determine these things. Now, as we then get them ironed out, we can go further on with getting tests done. So, enough of me talking nonsense. Let's have a look at our oscilloscope here and do a few little runs with the controller. Now, turn my ammeter on here. Fortunately, this only goes up to 600 amps, so let's see if I can drop this tripod down a touch just to get a better view of the scope, because fortunately I'm still saving up to get a DSO, so Probably be a Santa Claus job at the rate I'm going. Let's see if I can get that just in there a bit closer, so we can all see the damn thing as well. It's usually helpful, isn't it? Okay, so intensity. That was a good book, that actually. It was a Dean Koontz book. Intensity. Anyway, okay, there's some power coming on. So let us get some better resolution here. It's 500 millivolts per division. We're on a differential probe on a 1 to 20, by the way. So there we go. There's an initial run. Now, I'm not sure how well this is going to come out. If I crank the intensity up, I should be able to see the spike. We're at 73 amps on the motor side now. Should be able to see the spikes here. These are the inductive kicks from the transistor switching off. Now, very importantly to note here is that we don't have ringing, at least that we can see in this resolution. Sorry, my hand on the throttle isn't exactly the best here. Previously this was a ringing mess all the way to the full magnitude almost of the voltage, so that wouldn't have been good. Now, well, what we want to do now is we actually, there is ringing there or always will be, but what we want to do is to have a little bit of a look at that. So what we'll do, we'll give the controller some power. We're up at, well, let's take it up to 100 amps, 90, 100 amps. Now let's start cranking the time base up. Now, there is a ring there, as we can see, but a couple of things to note about it. The first is that it dampens down very quickly, which is good. Oh, I've done it again. Try and bring us back to 110 amps, close as I can get. So, and it's the magnitude and the rate at which it goes away that's very important. So I just give it a few little, pulse my throttle there a little bit. You can actually see if I go up to, there's 250 amps now. It's just the main spike that increases its intensity. What if I let the current back? If I go on again, the main part of the ring there on the left of the screen increases intensity, but the bus itself, which is what we're seeing here, is reasonably smooth. Now we'll crank our time base back down. You can see it come back. Now the other thing that I'm concerned with a little bit, and I think it's due to the fact that my bus capacitance is quite low, is that if we come in here and we see this is our DC voltage here, it's about 25-26 volts at the minute. Now as we increase the motor current, see what this is doing. It's starting to drop. This is due to bus capacitance. We're at 300 amps, 350, 400 amperes now. So we've got quite a steep drop in it. So that might be something that, this is the first time that I've employed film capacitors in a controller. So there's only about 760 microfarads on the bus at the minute, whereas prior to this I would have had anything up to I think on the 500 amp controller I had 3 4700 microfarad capacitors, so there's quite a lot of capacitance in there compared to what's there now. So that's something that we need to have a look at, but let's see. We'll see how the thing plays out. Now, just to I suppose someone's going to say I'm not putting out the current that I'm putting out, so I say I'm putting out, so we'll try and get the old Hope to be able to see my rather cheapy ammeter there. Unfortunately this only goes up to 600 amps, so I'm going to have to get something with a bit more welly than that. There's 500 amps, just over. It's as high as I'm prepared to go with that inductor bank at the minute. So I just have a nasty feeling that it would start having a bad hair day if I decided to push it much further, but that'll be for another day in paradise, as the song says. So I have our computer just set up with the RTD Explorer software over here as well. So we'll have a look at that, and you can just see how the you'll hopefully be able to see, says you, how the graphs follow each other. Now our heatsink temperature at the minute is at 29 degrees. There's no nasty hot spots on the transistors. Doesn't seem to be anything that's having a bad problem. Just see if I can zoom in a little bit. There we go. Hopefully that'll start coming out now in HD beauty. Yeah. Grab my throttle. What we're looking at there is we're looking at how the current reference and the current feedback follow each other. Actually, what I'll do is that let me just restart that program, because sometimes it slows down when and now it's just going to crash on me. So great, that was the fun of live cinema. Back in a minute. Okay, we're back. So give her some throttle. As we can see, the current reference, which is our throttle, and our current feedback, which is our motor current, following each other quite nicely. That's what we want to see. And it was actually this that led me to the discovery of the problem with the desat detection. Interesting. Looks like we had a desat event there for a second. Something we're going to have a look at. Anywho, there we have it. That's our controller now getting to a point where we can start to look at installing it in the car and actually having a bit of confidence in it, which is quite important to have. So what else have we got? Obviously my cells have turned up, so they need to be bottom balanced. So we have that going on. So we've work on the controller going on, and we're going to be working on another power electronics project now. Actually, I'm almost. It's going to involve some high power stuff. So yeah, that's about it, folks. not very exciting, but nonetheless has to be done to ensure that we can drive the car safely and with the power that is required of a car that large. So I would have liked to be able to go to with 1000 amps with this, and I might do yet before putting it in the car, but we have a few more things to iron out. But broadly the controller is functional, so that's the main thing. And we'll be back soon when we get some more work done. Yeah, that's pretty much it for the minute, and a couple of more things. I've got to do a pre-charging circuit on this as well. And also, hello Paul, I need the software that tells RTD Explorer what the actual current is and not 50% of it, thank you. So that's about it, guys. Back soon, and I'll try not to blow myself up.